We have been talking about the central limit theorem and how we can use that to estimate means and standard deviation for sample distributions. We can apply the same concepts to proportions. So some notation to start with. A population proportion, P, is the fraction or percentage of a population that has a certain characteristic. So for example, if we said something like 90% of adults carry a cell phone, 90% or 0.9 would be our P, our population proportion. And then a sample proportion, we call it P hat, is the fraction or percentage of a sample that has that same characteristic. So some notation here. We have population proportion is just P is X over N. So N is the number of elements in the population. So if we were doing like, the citizens of Bryan or something, okay, N would be all of the citizens in Bryan, and then the X would be whatever it is we're looking for, how many of them are female or whatever. And then a sample proportion is given by P hat, and that's X over N. So this is if we're taking a sample. So instead of all the citizens of Bryan, maybe we just survey 100 of them, and we're seeing how many of them are female. I don't know, whatever we're doing. But lowercase n is the number of elements in the sample. So we'll see that notation throughout the rest of the year. You just need to be familiar with the difference between those. So if we want to use the central limit theorem, we have to meet some conditions for this. They have to be simple random samples. We have to have the conditions for the binomial distribution. So that means they're independent trials, a fixed number of them, only two possible outcomes. That's important. The probability of success for one of the outcomes is P, and the probability for the other outcome is 1 minus P. And then the sample size has to be enough that both of these are true. So make sure you highlight that, circle it, star it. There may be some problems on your homework that ask, like, is this sample size large enough? And so to see that, you have to do n times p. That has to be greater than or equal to 5. And then n times 1 minus p also has to be greater than or equal to 5. So if all of those conditions are met, we can use the central limit theorem. And mu of p hat is going to be equal to p, just like mu of x bar was equal to mu. And then sigma of p hat, the standard deviation is going to get smaller. And we have an adjusted formula for that, which is the square root of p times 1 minus p over n. Along with both of those being adjusted, we have an adjusted z-score. So remember, normally when we do z-score, it's x minus mu over sigma. When we were using the central limit theorem, we had just some adjustments, and the big one was it was sigma over root n. Okay, so that's what we did in 7.1 and 7.2. This adjusted z-score is for proportions. So it's going to be p hat minus p over the square root of p times 1 minus p over n. Okay. All of those are on your formula sheet. So again, you don't need to memorize these. You just need to recognize when you need to use this. And it will say in the problem, you'll know that it's proportions because it's going to talk about proportions, whereas our other problems we're talking about means. So I'm going to show you how to do this one by hand, and then I'll show you how to do stuff on the calculator. So in a certain conservative precinct, 79% of the voters are registered Republicans. We can pretend this is Williams County because that's probably just about accurate. We want to know what's the probability that in a random sample of 100 voters, at least 68 would be registered Republicans. So we're going to just draw this real quick. Okay, so we know that 79% of our population is registered Republicans, and we want to know the probability, our p hat, the p hat that we're looking for in our sample. We want to know if 68 out of 100 of them are going to be Republicans. So that's going to be 0.68. So that's down here somewhere. It doesn't really matter where. And we want to know at least, so we want to find this area. Okay. So in order to use the table, we're going to need to find the z-score. So our z-score is p hat minus p over the square root of p 1 minus p over n. So p hat, we just said, was 0.68. P comes from the population, that was 0.79. And then we have the square root of 0.79, 1 minus 0.79, and our sample size was 100. Now, when I'm doing this in my calculator, I'll often do the parts like underneath the square root first, and then take the square root of it, and then finally do the numerator divided by that answer. But however you get into your calculator, you can do it all at once in your calculator if you do parentheses like that. I think we get negative 2.7. So we want to find the probability that our z-value is greater than, because remember I shaded above, greater than negative 2.7. Now, if we're using the table, remember the table only gives us area below, so we're going to have to do 1 minus probability that it's less than negative 2.7. And that's what we'll look up in the table is negative 2.7. And when we do that, we get 0.0035. And so that is 0.9965. Okay, so that is how we adjust for doing a proportion. And we can use the table for that. We just have to use our adjusted z-score and look things up in the table. In the next video, I'll show you how to do this with a calculator.